Welcome to G Fun Facts Online. If carbon's benzene is the lord of the rings of the chemical world, hexasilabenzene was its mythical, arguably cursed sister. For decades, it was the subject of fierce and often pessimistic debate among computational theoreticians. To understand why, we have to look at how these elements behave at a fundamental level. While carbon forms a perfect, flat, regular hexagon known to chemists as D6H symmetry, quantum chemical calculations consistently warned that a flat ring made entirely of 6 silicon atoms and 6 hydrogen atoms would be a highly unstable transition state. Carbon and silicon sit right next to each other in the same column of the periodic table, so you might naturally assume they behave identically. But silicon is a larger atom. Its electron orbitals are much more diffuse, and it struggles to form the tight, continuous pi bonds that give carbon rings their legendary, rock-solid stability. This inherent weakness of the continuous silicon-to-silicon pi bonds, combined with a quantum mechanical phenomenon known as the pseudo-John Teller effect, meant that the ring would spontaneously buckle just to relieve immense internal molecular stress. Theoreticians predicted that hexasilabenzene would inevitably contort into a puckered, chair-like configuration, much like the molecule cyclohexane, or it would collapse entirely into a prismane structure, which is essentially a three-dimensional triangular prism, to maximize the number of stable single bonds. For years, experimental reality matched this highly pessimistic math. The only isolable 6-silicon species synthesized back in 1993 was indeed a non-aromatic, completely non-planar hexasilaprismane. The grand dream of a flat, Huckel aromatic, fully silicon-based benzene seemed outright forbidden by the fundamental laws of physics. But in January 2010, the chemistry world was completely blindsided by a stunning breakthrough published in the prestigious journal Science. A research team led by David Sheshkowitz, alongside Kai Abersfelder, Andrew White, and computational chemist Henry Rzepa, announced that they had finally synthesized a stable isomer of hexasilabenzene. To achieve this seemingly impossible, they utilized a meticulously chosen, extremely bulky molecular precursor known as the 2,4,6-triisopropylphenol group, or simply the TIP group for short. Think of these TIP groups as massive molecular bouncers, shielding the incredibly fragile 6-silicon core from reacting with its outside environment. The resulting compound materialized as intensely green crystals that were shockingly stable. They could be exposed to the open air as a solid for hours and dissolved in solution for minutes without degrading, which is an absolute eternity for an exotic, highly reactive silicon compound. But when crystallographers beamed X-rays through these green crystals to map out their exact atomic structure, they were astounded by what they saw. The molecule was not a flat hexagon, it was not a puckered chair either. It was a highly unusual, mind-bending tricyclic architecture. Inside this bizarre ring, the 6 tip substituents were not distributed evenly with one on each silicon atom, as they are in regular benzene. Instead, through a rapid molecular 1-2 shift during the synthesis process, the silicon atoms had rearranged themselves completely unevenly. 2 of the ring's silicon atoms carried 2 substituents each, 2 silicon atoms carried 1, and incredibly, 2 silicon atoms carried absolutely no external appendages at all, existing as completely naked vertices. At first glance, this uneven, chaotic distribution suggested that the continuous, unbroken network of pi electrons required for classical aromaticity was totally destroyed. However, the data told a different, much more complex story. Nuclear magnetic resonance spectroscopy of the silicon-29 isotope revealed highly dispersed chemical shifts ranging wildly from +125 to -90 parts per million. This massive spread indicated a highly inhomogeneous electron distribution. The silicon atoms within the exact same ring were exhibiting entirely different formal oxidation states of +2, +1, and 0. Yet, when Rzepa and Sheshkowitz ran exhaustive quantum theoretical analyses on the central 4-membered ring of the structure, they found hidden elegance. Despite the distorted geometry and the dismutation of oxidation states, there was a robust cyclic delocalization of 6 mobile electrons, made up of an exotic cocktail of pi, sigma, and non-bonding electrons, continuously flowing right across the central framework. The ring was undeniably stabilized by this electron flow. Sheshkovitz and Rzepa coined a brand new term for this unprecedented phenomenon, calling it dismutational aromaticity. Hexasilabenzene hadn't failed to be aromatic. It had simply found a completely novel, three-dimensional loophole in the strict laws of quantum chemistry to achieve it. This discovery dramatically expanded the very definition of chemical stabilization, proving that Huckel's 4n+2 rule could manifest in ways previously unimaginable. While the discovery of dismutational aromaticity was a magnificent scientific triumph, the thirst among chemists for a truly flat, continuous silicon ring remained unquenched. If neutral silicon molecules simply refused to stay flat due to the pseudo-John Teller effect, what about charged versions of the ring? Computational studies on anionic, or negatively charged, silicon cycles, particularly those incorporating lithium, offered a powerful glimmer of hope. Density functional theory calculations suggested that if you pumped extra electrons into the system, the geometry would fundamentally shift. In a theoretical series ranging from psi6Li2 to psi6Li8 structures, the absolute global minimum of energy was actually a perfectly planar ring possessing highly symmetric D2H geometry. Experimental hints of this began to emerge when scientists probed solid-state Zintel phases and found solid-state NMR evidence of perfectly planar, aromatic silicon rings hiding deep within the crystal lattice. Driving this frontier forward, Sheshkovitz's group at Saarland University continued to innovate, pioneering the chemistry of silicanoids. Silicanoids are unsaturated, partially substituted silicon clusters that intentionally feature those naked, unsubstituted silicon vertices, echoing the highly reactive surface of bulk silicon. By chemically reducing their famous dismutational hexasilabenzene isomer, the team generated a highly nucleophilic anionic silicon cluster. This cluster behaved remarkably like a silicon analog of phenyllithium, which is a ubiquitous and vital reagent in organic chemistry. This proved that not only could these exotic, naked silicon clusters exist, but they could also be used as powerful, intact building blocks to transfer the core structure to other chemical frameworks, bridging the gap between theoretical curiosities and functional, synthetic reagents. This 50-year quest reached yet another staggering crescendo in the early months of 2026. For half a century, chemists had chased not just the benzene ring, but other iconic aromatic architectures. Among the most famous is the cyclopentadienyl anion, a flat 5-membered carbon ring carrying a negative charge and 6 pi electrons. It is an absolute cornerstone of organometallic chemistry, famously used to create sandwich complexes like ferrocene that revolutionized modern industrial catalysis. In a mind-boggling twist of fate, and a true testament to the global collaborative nature of this scientific pursuit, 2 independent research groups achieved the unthinkable entirely simultaneously. A team led by David Sheshkovitz at Saarland University and another team led by Takeaki Iwamoto at Tohoku University in Japan synthesized the exact same elusive molecule via completely different chemical routes. They had successfully created the pentasilacyclopentadienide anion. Published back-to-back in Science, this breakthrough revealed an all-silicon, 5-membered aromatic ring that entirely defied classical organic expectations. Unlike traditional carbon aromatics, which comfortably settle into a static, stable resonance hybrid where electrons are smeared evenly across the ring, this purely silicon ring was found to teeter dynamically on the absolute bleeding edge between resonance and equilibrium. It was a living, breathing molecule whose bonding framework constantly fluctuated, offering scientists a real-time, unique glimpse into the fundamental phenomena of chemical bonding at the very edge of stability. The isolation of this chemical required masterful crystallographic work and ultra-precise electron counting, proving that highly metallic elements can indeed sustain robust aromatic systems if coaxed with the exact right balance of steric bulk and electronic charge. It is incredibly easy to look at the synthesis of hexasilabenzene and pentasilacyclopentadienide as purely academic flexes, just a group of brilliant chemists dedicating 50 years to rewrite a few pages of advanced chemistry textbooks. But the implications of this quest extend far beyond theoretical satisfaction. They are the gateway to an entirely new era of materials, science, and industrial technology. Because silicon is inherently more metallic and polarizable than carbon, its aromatic analogs possess drastically different and highly desirable electronic, optical, and catalytic properties. For instance, computational and spectroscopic studies show that silicon analogs of polycyclic aromatic hydrocarbons exhibit extraordinarily large non-resonant, second-order optical hyperpolarizabilities. In plain terms, these molecules interact with light in highly exotic ways, making them prime candidates for the development of advanced infrared nonlinear optical materials, which are absolutely critical for next-generation telecommunications and advanced photonics. Furthermore, the successful stabilization of highly reactive, electron-rich silicon centers opens the door to a holy grail of industrial chemistry, which is metal-free catalysis. Currently, massive global industrial processes, from the production of critical pharmaceuticals to the creation of advanced polymers via olefin metathesis, rely heavily on rare, extraordinarily expensive, and environmentally toxic transition metals like palladium, platinum, iridium, and ruthenium. The extraction of these metals leaves massive carbon footprints and destroys ecosystems. However, researchers have noted that the exact same principles of steric shielding and electronic manipulation used to stabilize silicon aromatics could be applied to design robust, entirely silicon-based organocatalysts. Silicon is the second most abundant element in the Earth's crust. We are looking at a very real future where the completely abundant sand beneath our feet could be chemically transformed into sophisticated, unbelievably cheap, and non-toxic catalysts that entirely replace the world's reliance on precious metals. The isolation of stable silicon double bonds in aromatic rings also feeds directly into the booming trillion-dollar field of two-dimensional materials. Hexasilabenzene and its various isomers are fundamentally the smallest possible molecular fragments of silicene, which is the silicon equivalent of graphene. While graphene is perfectly flat, theoretical physicists have long predicted that silicene naturally wants to adopt a buckled, corrugated structure due to the exact same pseudo-John Teller effects that make hexasilabenzene buckle. Understanding the delicate mechanics of pi electron delocalization and dismutational aromaticity in these isolated ring systems provides physicists with the exact chemical blueprints needed to manipulate and tune silicine's electronic band gap. Moreover, the ability to synthesize long-chain polymers containing double bonds between heavier elements points toward the creation of unprecedented optoelectronic materials. These heavy element conjugated polymers could revolutionize the manufacturing of organic light-emitting diodes, highly flexible solar cells, and smart materials whose electrical conductivity and optical emission can be finely tuned simply by altering the underlying silicon ring framework. The 50-year quest to rewrite chemical ring theories through the pursuit of silicon aromatics is a profound testament to human perseverance and the scientific method. It is a story that began with a rigid, prohibitive rule, the double bond rule, that explicitly told scientists what nature would simply not allow. Through the pioneering kinetic stabilization strategies of scientists like Robert West, the structural brilliance of Norihiro Tokito, and the paradigm-shattering boundary-pushing discoveries of David Sheshkowitz and Takaaki Iwamoto, the absolute boundaries of the chemically possible were forcibly expanded. The journey from the fleeting cryogenic ghosts of early silabenzenes to the vibrant green crystals of dismutational hexasilabenzene, culminating in the dynamic resonance of pentasilacyclopentadienide, perfectly encapsulates the beautiful and often surprising interplay between theoretical physics and experimental audacity. By forcing silicon to dance to the tune of aromaticity, chemists have done much more than honor August Kikulé's ancient Ouroboros dream of the benzene ring. They have permanently broadened the canvas of molecular design. They have proven that the rigid rules of the periodic table are sometimes just waiting for the right level of human ingenuity to break them, ensuring that the future of advanced materials, sustainable catalysis, and fundamental chemistry will be limited only by our imagination. Thank you for tuning in to G Fun Facts Online. Keep wondering and keep discovering.